Alrighty, next part I'm going to do is I'm going to do an object. Instead of being on a flat surface, we're going to do this object where it's on a steep incline. So let's do that. First thing I'm going to do is I'm going to draw my object being on a steep incline. Give me 1 second. Alrighty, here's I got my box. If it's on an incline, this incline angle we'll call theta. So first thing I'm going to do is anytime you're given a force question, first step is going to be draw your free body diagram. So I've got my object right here. First thing I'm going to do is draw my free body diagram, and that's going to be weight is going to go straight down. Force normal is going to be perpendicular to the board. And then if the object wants to slide to the right, meaning my motion wants to go down, that means frictional force is going to be up the board. Anytime you do this in class, you're immediately going to take your free body diagram, bring it off to the side, and redraw using the components. So what I'm going to do now is I'm going to redraw those forces and then leave my object behind. So I've got weight downwards, I've got force normal, and then I also have frictional force up the board. What I'm going to do now is include my components. So my components are going to be, we're going to call this weight perpendicular to the board, because it's the forces that's going into the board. And then you're going to have weight parallel. So this is weight that's parallel to the board and the way it wants to move. With this, I can now do my equilibrium statements. Let's say this object is accelerating, so it is sliding down. So let's say that if our object is accelerating, we'll call that acceleration positive and to the right. So that means the summation of my forces is going to equal something to cause that acceleration. Well, if we have a box that's sliding down a board, it's safe to say that it's not going to fly magically in the air or crashing through the board. So we're looking at more of the frictional force and that weight parallel and how those play. So what I can then say is for force applied, I'm going to say parallel to the board versus forces applied perpendicular, okay, to the board. This is because my frame of reference is looking at parallel versus perpendicular to the board. So perpendicularly, we can say that force normal of the board is going to be equal to weight perpendicular. And then up here, when parallel, we can say that mass times acceleration is going to equal to weight parallel minus frictional force. Well, how do we know this? Well, if my object's going to be accelerating, what is going to be causing that acceleration? And that's going to be weight parallel. And what's slowing down that acceleration is frictional force. If I said acceleration was over here, if I said it was negative, I would have written this backwards. I would have written this as mass times acceleration equals frictional force minus weight parallel. But I told you the acceleration was positive and to the right, so that means my force going to the right overall is going to be larger than frictional force. From here, we can make a little bit more of, do a little bit more trig magic. So we got the angle here is theta. All right. Now, what some people have a hard time with is dealing with parallel and perpendicular lines, a little bit of geometry. So what I'm going to do over here is very briefly, I'm going to explain why this angle theta is equal to this angle of theta. If I have two lines that are parallel to a line that is perpendicular, so if we looked at this and we called this line one, we called this line 2. So if I said these two lines were parallel to this intersecting line, what I can then say is this angle right here would be equal to this angle on the inside. Now that got a little ugly, so let's try that again. we're trying to see how this angle right here relates to this angle right here. So what I'm going to say is, let's see if we can draw it over here, and this will be a little bit better. If I have two parallel lines intersected by an angle of theta. Now, that angle theta is going to be the alternate interior angles theorem of what you're going to use back in geometry class. So where this angle is going to be right. Let me see if I can get this right. Oh, nope, it's not working out quite right. So we're going to bail on that, and we're just going to say that this angle theta is equal to that angle theta. I have a little bit of a hard time drawing on this thing. We're just going to call that inexperience, and then we're going to keep moving forward. So with our little bit of a trig magic, we can then say that if this is my angle theta, so that sine of theta equals weight parallel over weight, and that cosine of theta equals weight perpendicular over weight. I can then use this over here and say MA equals weight sine theta minus frictional force, which is going to be mu sub k, times force normal. And then down here, I'm going to say force normal equals weight times cosine of theta. You're usually going to use these two statements right here in your final calculations for whatever you're looking for if your box is hanging off of or going down a ramp. All right, next we're going to do is half Atwood machine. Half Atwood machine is an object that is hanging off of a table that is suspended by a massless, stringless pulley. So give me 1 second, I'm going to draw that. Alrighty, let's draw the Freebody diagram of this system right here. So overall, both of these are going to have weights. So let's call this mass 1, and let's call this mass 2. And what we're going to say is mass 1 is going to be much greater than mass 2. Let's go ahead and draw this, and we'll call, since mass 1 is much greater than mass 2, and we'll say that friction does exist, so we're going to call the acceleration of this system as 0. Alright, let's see what we got here. Well, let's do our forces of our free body diagram in blue. So we're going to have weight downwards and tension upwards. Since I have different masses and different weights, you're going to annotate this as weight 2. Over here, we're going to have weight 1, force normal, frictional force, and tension. What this allows me to do is now I can write my equilibrium statements. Since none of these are at angles, let's go ahead and move this off to the side, not touch it one bit. Let's rescale that. There we go. And move it off to the side. So here's what I can say. I can then say that for my two boxes, I'm going to draw each box individually. We'll call this mass 1, we'll call this mass 2. What I can say is for force normal is going to be equal to weight of the first box, since it's not accelerating, so my summation of my forces in the y direction are going to equal 0. So that means weight 1 equals force normal. What I can also say is that tension is going to be equal to frictional force, because the summation of the forces in the x direction are going to equal 0. So that means tension equals frictional force. Over on the other side, we're going to be able to say is looking at weight and tension, that the summation of the forces in the x and the y direction are going to equal 0, since my object's not accelerating. we're going to say it's not moving. So in the y direction, that means going to be weight 2 is going to be equal to tension. We could break this up a little bit and transfer tension over, so let's do that. Weight 1 would be m1g times force normal. Tension would equal frictional force. That could be mu sub s, since it's not moving, times force normal. And over here, weight 2 would be m2g equals tension. So what I could do is plug this into this, and then plug this into that. That will allow me a system of equations so I can say overall, holistically, what's going on. Let's see what kind of magic we can get into. So over here, if I plug this first equation into the second one, you get tension of your object equals mu sub s. Try that again. Mu sub s times m1g. I can then plug this on over here. So I can say m2g equals mu sub s m1g. And then we can say if we want to solve for static friction, we can say mass 2 divided by mass 1 would be our answer. Alrighty, that's all we got.